All right, let's go ahead and get started. So to introduce myself, I'm Professor Blocky. I'm an assistant professor here in the computer science department. You probably already know me as the guy that introduces the speakers before each seminar, but today I'm giving the talk. So my research interests really include passwords, cryptography, data privacy. Today I'm going to tell you about memory hard functions and their applications to password hashing. All right, so let's just motivate the problem. What is a password hash function? So let's think a little bit about what happens behind the scenes when you log into a website like Amazon.com or PlayStation.com. So here I am logging into PlayStation.com. I have my username, jblocky, and a password here, 123456. Now I promise you that's not my actual password if anyone is trying to log into PlayStation.com right now. But for the example, let's say my password was 123456. Well, what does PlayStation.com do? They'll take my username, they'll pick a random value, which is often called a salt value, and they're going to append this random value to my password. And then they'll take a cryptographic hash function, something like SHA-1, SHA-2, SHA-3, and they're going to hash my password with this salt value appended to it. And what they'll store on their server is just this hash value, this garbled string. So later on, if I try to authenticate, I'll send them my username, I'll send them a password guess, and they'll just regarble this password guess, check to see if it matches the hash value on file, and if it does, I authenticate. If it doesn't, try again. Okay, so this sounds like a great solution. What can go wrong? Well, oftentimes due to programmer errors, server misconfigurations, failure to update your patches, hackers are able to break into this server and actually steal all these hash values. Right. So in this case, an attacker breaks in. He sees this file which has my username, my salt value, and the hash of my password. Once he has the hash of my password, he can check as many guesses as he wants offline. He no longer has to interact with PlayStation.com. He can continue trying guess after guess after guess, trying to crack my password. So in particular, maybe he thinks my password is password, so we'll hash password. He'll append the salt value to that string and hash it, check to see if it matches. Next popular password, 123456. He'll append the salt value, hash it, and check to see if it matches. In this case, he's cracked my password. All right, so the only thing limiting an attacker in an offline attack is just the cost of computing this hash function. So the attacker will start with a popular dictionary, of common user passwords, and he'll just, enumerate through every password guess in this dictionary, compute the hash each time, and just check to see if it matches. So the point here is that there's no locking the attacker out, right? There's no limit. You can't say you've tried 3 guesses, you've been wrong all 3 times, you're locked out. The attacker here has this hash value, so he can continue guessing without getting locked out. All right. And offline attacks are unfortunately a common problem. So password breaches at major companies have affected millions of users. So here we have a wall of shame. We've got LinkedIn, Sony, RockU, Adobe, Yahoo, Living Social. And this is the wall of shame that just keeps growing and growing. So over time, I have to add more and more examples to this list, and you can probably find some notable examples that are not present here. I didn't include Equifax up here because it's not clear whether Equifax actually involved passwords. So this list is only password-related breaches, though the Equifax breach was also a particularly notorious one. And I should mention that I'm going to have to update my slide again now because it says millions. And if you saw the news story this past week, Yahoo just upgraded their estimate of how many user accounts were hacked in their breach from 1 billion to 3 billion. So now this slide should actually say billions of user accounts affected. All right, so offline attacks are not only a common problem, they're also a dangerous problem. So This machine here, it's called the Antminer S9. It's one of the mining rigs that people use to mine Bitcoin. So to mine Bitcoin, you have to compute the SHA-256 hash function over and over and over and over again. Well, if you look at the specs for this machine, it says 14 TH per second. What does that mean? It means that this little machine is computing 14 trillion SHA-256 hashes per second. Now that's a pretty impressive number. And what makes this even more concerning is this machine is not particularly expensive. If you have $2,000 sitting around right now, you could go on Amazon and you could actually buy one of these machines. So the other piece of the threat is, you have a machine that can compute SHA-256 14 trillion times per second, and users are still picking fairly predictable passwords, right? So it's 2017, and the most common passwords are still, password 123456, 12345678, fairly predictable stuff. This doesn't mean that every user picks, such a weak password, but the entropy of user-selected passwords is still low. So one of the key challenges in password hashing is, can we actually increase costs for the attacker, right? If the attacker is able to try 14 trillion guesses per second, then he's going to just, demolish most passwords and crack, most user passwords in just a fraction of a second. So really what we want to do is we want to increase the cost to check each password guess, which means we somehow want to make this hash function more expensive for the attacker to compute. So how do we do that? Well, one attempt that's actually been tried, and to Yahoo's credit, they actually started using bcrypt. Bcrypt is, instead of using the SHA-256 hash function or some other hash function, you'll take the hash function, you'll compute it once, and then you'll apply the hash function to that hash value, and you'll just iterate many times. So for example, PBKDF2 is just iterating the SHA-256 hash function over and over and over again. And when LastPass was breached, they were using PBKDF2 with over 100,000 SHA-256 iterations. Right, so just to check one password guess, the attacker has to compute SHA-256 over 100,000 times. Now, unfortunately, this still may not be enough to defend against an attacker that has customized hardware, like this Antminer S9. So in particular, if the attacker builds, an application-specific integrated circuit whose job is just to crack the user's password, then, we would estimate that this ASIC would be able to try about 140 million password guesses per second. And if you, amortize over hardware cost, energy cost, this would translate to about $1 per billion password guesses. Right, so that's still pretty cheap, right? The cost per guess is still marginal. All right, so here's the challenge, right? We have, on the one hand, over time, the cost of computing a hash function, let's say SHA-256, is steadily decreasing as people develop customized chips to actually compute this function. On the other hand, user patience is remaining fairly constant, right? Over time, user patience is pretty steady, which means that you can't just, start increasing the number of hash iterations over time. One solution would be, instead of 100,000 iterations, try, 100 million hash iterations. But okay, now the problem is you're going to require the user to wait, 10 to 100 seconds just to authenticate, right? The user types in his password, you have the computer compute this iterated hash function, and 10 seconds, a minute later, it gets back to you, your password was correct, or hopefully you didn't make a typo, and then it says your password is incorrect, and now you have to wait another minute to check your second guess. Right, so the challenge here is that we're really constrained in the amount of time that we can take to hash a password. Right, users are not willing to wait for a minute or longer. really, realistically, you're talking about maybe half a second to a second of time to perform key stretching before users are going to start to complain. Okay, so now our goal is to develop a moderately expensive hash function. And it should have the property that it's reasonably fast for the user to compute on standard hardware, let's say your personal computer. And it should also be expensive for the attacker to compute, even if the attacker builds customized hardware, like an application-specific integrated circuit. Now, these properties might sound contradictory, and there is a tension, right? If it's fast to compute on your computer, well, certainly after the attacker builds customized hardware, the cost per guess for the attacker is not going to be any lower than the cost per guess for the legitimate user, right? After all, the attacker just gets to build customized hardware to optimize this task. So how can we, hope to achieve this goal? How can we hope to have a function that is computable by the user in, let's say, under a second? And at the same time, it's economically prohibitive for the attacker to try millions or billions of guesses per user. So this is where memory hard functions come into play, right? So the idea of a memory hard function is you want to design a function where computation costs are actually dominated by memory. So if you want to just compute, SHA-256 a million times, all you have to do if you're an attacker is build an application-specific integrated circuit. The size of the chip or the core that computes SHA-256 is going to be pretty tiny. And you just have to lock this chip up for a fraction of a second, and then you're done computing this function. The idea of a memory hard function is instead of forcing the attacker to just lock up a tiny chip, why not force the attacker to lock up an entire DRAM chip filled with, let's say, a gigabyte or more of memory? So the idea here is we want to force the attacker, if he wants to compute this function once, we want to force him to lock up, let's say, a gigabyte of memory for the duration of computation. Right, so we want to force this attacker to lock up large amounts of memory, basically for an entire second or half second or however long we're performing this computation. Right, and I claim that this means that the function is still going to be expensive even on customized hardware. Why is that? Well, two reasons. You can optimize programs by building customized circuits, but really the cost of memory on an ASIC is roughly the same cost that you would pay to put that memory on your personal computer. So the attacker is not really going to be able to improve latency or bandwidth or just the cost of the physical cost of that DRAM chip. He can't reduce that cost by building customized hardware. That cost is constant and equitable across architectures. Okay, so we want this function to be memory-wise expensive. So how do we do that? Well, there's one candidate function called SCRYPT, which basically starts to fill memory, and then you access random points in memory and kind of garble it up a little bit and make a pass over memory in a randomized fashion. And SCRYPT actually does seem to be memory hard. Now, SCRYPT does have a downside on the other hand. In particular, SCRYPT accesses memory in a data-dependent fashion. That means that if you input the password 123456 and then just observe the pattern of memory accesses, that pattern is going to be different than the pattern that you would get if your password had been password. Right? So an attacker who can mount a side channel attack, let's say he's sitting on, he's executing a process that's sitting physically on the same machine. If he can just make some cache timing measurements, he can actually learn a little bit of information about that memory access pattern of the hash function. And if he can learn a little bit of information about the memory access pattern, then potentially he's learning information about the password itself. Right, so SCRYPT has some nice properties, but it also is vulnerable to side channel attacks. So for most of the talk, I want to tell you about an object called data-independent memory hard functions. What does data-independent mean? Data-independent means that the memory access pattern is the same regardless of input. So whatever input you give to the hash function, the memory access pattern is going to be the same. So in this case, an attacker that's sitting there measuring cache accesses is not going to be able to learn anything in a provable sense about your password, because that memory access pattern would have been the same whatever password you input. All right, so the point here is that now if we have a data-independent memory hard function, this function is no longer vulnerable to side channel attacks. All right, so due to the recently completed password hashing competition, which started in 2013 and finished in, I believe, summer of 2015, we have lots of candidates for data-independent memory hard functions. Some of the prominent ones, there's a function called Catena, which received special recognition at the password hashing competition. And there are a couple different variants of the Catena hash function, Dragonfly, Double Butterfly. You've also got Argon2, which was the winner of the password hashing competition. So this is a particularly important memory hard function to understand. Originally, when Argon2 was announced as winner, the designers of Argon2 were suggesting using the data-independent mode for password hashing. That recommendation has changed, and we'll see why a little bit later. But originally, when they won the competition, they were recommending use the data-independent mode of operation to hash passwords. This is so that you're not vulnerable to side channel attacks. There's another newer proposal, which was developed by some researchers at Stanford, called balloon hashing. Here, the design is actually fairly similar to Argon2, but they made a few tweaks that allowed them to actually prove some nice security properties. So it's a newer proposal, but structurally pretty similar to Argon2. Okay, so these are some of the iMHF candidates. How does an iMHF work? Well, an iMHF is defined by two things. You have a hash function h. Think of SHA-256 or SHA-3, and then you have a directed acyclic graph G. So directed acyclic graph, it's just a graph. You have nodes, edges between nodes, but all of these edges are directed, right? So in particular, we can label these nodes 1 through n, and an edge goes from the earlier node to the later node, right? So if you have an edge between nodes 10 and node 100, the edge will go from node 10 to node 100. Okay, so what does this directed acyclic graph mean? Well, essentially, the directed acyclic graph encodes data dependencies, right? So each node here corresponds to an intermediate data label that's produced during computation, and edges basically specify that label 4 depends on data label 2 and data label 3, right? So in particular, the first label is just the hash of the input, the password and the salt. Then an intermediate label is the hash of its parent labels, right? So to compute this label, I'm going to hash this value and this value and hash them together, and that gives me label 3. Then to compute label 4, I'm going to take these values, hash them together, and that gives me label 4. All right, so that's basically how a data-independent memory hard function works. The final output then is just the label of the last node. So in this case, right, we have a 4-node graph. So the output is just the final label in this graph. Okay. So now we have this graph. We've defined this function. How do we evaluate this function? Well, to evaluate this function, we can introduce a helpful abstraction called graph pebbling. The idea of graph pebbling is as follows. So you start off with no pebbles on the graph, and then at time I, you can place a new pebble on the graph if and only if you had pebbles on all of the parents of that node in the previous step. Basically what this is saying is, right, if you place a new pebble on the graph at time I, then at the previous step, you better have had all of the dependent data labels already stored in memory. Otherwise, there's no way you could have computed this new label. right? And then the final constraint here just says that you have to finish. So you have to compute the final output label, which means that at the end of this pebbling, you better put a label on this last node, because that's your output. So here's a simple example of pebbling. So we start with no pebbles on the graph. At time 1, I can place a pebble on node 1 because node 1 has no parents. So I can just compute this label and store it in memory. Then at time 2, since I already have a pebble on node 1, I can place now a pebble on node 2 because all of its parents were in memory. Now notice that I have pebbles on the parents of node 3. Parents of node 3 are nodes 1 and 2, so I can now place a pebble on node 3. At the same time, I don't have to keep pebbles on the graph. So in this example, I discarded pebbles on nodes 1 and 2. Why did I discard those pebbles? Well, it's to save space, right? To keep these data values in memory, I need to allocate a certain amount of RAM. If I can just discard these pebbles, that corresponds to freeing those corresponding memory values, right? So in this case, I'm keeping memory usage low by discarding those pebbles. Then I'll place a pebble on node 4. Once I have pebbles on nodes 3 and 4, I can place a pebble on node 5. And that's it. So that's how you evaluate this function. And here, placing a pebble just means computing the hash function. All right, so that's the pebbling game. Now the question is, how do we actually measure the cost of computing a memory hard function? And the first measure that might come to mind is something called space-time complexity. So here you're looking at how much space does this algorithm use, and multiplying by the number of pebbling rounds, right? So this term over here is the maximum number of pebbles on the graph at any point in time, and then this term over here is just the total amount of time that it takes to pebble the graph. So this equation is telling you how much space do you need to allocate in the worst case, and multiply that by the total number of steps, and that gives you space-time complexity. So space-time complexity is a nice measure of complexity, and there's a rich theory underlying this measurement. But I claim that this is not the right measure for password hashing. Why do I claim that? Well, the problem is with amortization, right? So for a parallel attacker, space-time complexity can actually scale badly in the number of evaluations of the function. Here's a simple example. Right? Let's suppose that this blue area plots, number of pebbles on the graph over time, right? So initially, as I'm pebbling this graph, I have to use a lot of pebbles. And then after a little bit of time passes, I can discard most of these pebbles from memory, but then I have to keep pebbling this graph until I reach the end node for a long time, right? So in this case, the space-time complexity would just be the area, or this bounding rectangle around this blue curve, right? So you'll notice that this area around the blue curve in this case is much larger than the area under the blue curve. Why is that a problem? Well, the attacker doesn't just want to compute this function once. The attacker wants to compute this function hundreds, thousands of times. So what happens if instead of just doing this one time and then repeating, what happens if the attacker starts computing this function on the first input, and then as soon as you drop to a low space state, you start computing the second instance of this function. Then you wait till you drop to a low space state again, and then you start computing the third instance of this function. In this case, the area around this space is increased, but just a tiny bit, right? It's basically the same area to bound all these curves, right? Which means that in this case, the cost of computing this function once is roughly equal to the cost of computing this function 3 times in the example, right? So in this case, the attacker managed to do 3 times the amount of work, check 3 password guesses, but the attacker's costs didn't really increase at all. So this is not a particularly good property for a password hash function to have. And in particular, if all we're doing is trying to measure space-time complexity, we can't guarantee that the attacker won't be able to amortize his costs. And in general, Allwin and Serbanenko pointed out that there exists, functions where, the amortized cost of computing this function is square root n times smaller than the cost of computing it once. Right, so if you compute this function square root n times and then amortize, basically you're still paying the same total costs that you would pay to compute this function once. Right, so this was just kind of a theoretical example, but it does illustrate that there might be a concern if we're using space-time complexity to measure the effectiveness of our password hashing algorithm, there might be problems later on down the line. To overcome these problems, Allwin and Serbanenko introduced a separate measure called cumulative complexity. And basically, the cumulative cost of pebbling a graph G is just the area under this curve. Right? So if you have a pebbling strategy, instead of taking the area of this bounding rectangle, just take the area under this curve. Right? So instead of bounding, you just take the area, or you can think of this as the integral of space usage over time. Okay, so why is this a better measure? Well, for one thing, guessing 2 passwords now actually doubles the attacker's cost. Right? So if we're measuring the cumulative cost of pebbling this graph, if we want to pebble 2 copies of this graph, then that's twice the cost of pebbling a single copy. Right, so actually we do get a nice amortization property. Right, the cost of checking 1,000 password guesses is going to be 1,000 times the cost of computing 1 guess, which is exactly what we want. Okay, so back to our example. Here was our pebbling. Right, if I was computing space-time complexity, I would take maximum space usage multiplied by time. So in this case, we have 5 steps. Maximum space usage is 2. So in this case, the space-time complexity would be 10. But the cumulative cost here would just be 7. So we're just going to sum up, all of these rounds. So we have 1 pebble plus 2 pebbles on the second round, plus 1 pebble on the third round, plus 2 pebbles on the fourth round. And if we just add it up, we'll get 7. So in general, the cumulative cost of pebbling a graph is lower than the space-time cost of pebbling a graph. So what we want is we want to design a graph where the cumulative cost of pebbling this graph is high, not just the space-time cost. We want to make sure that the cumulative cost of pebbling this graph is high. Okay? So just to reiterate, what are our goals now? We want to find a graph G on n nodes such that this graph has constant in degree. The reason I ask for constant in degree is just for practical reasons, right? To actually place a pebble corresponds to computing the hash of dependent data values. If the number of dependent data values is too large, then really that's not constant time to place a new pebble on the graph. So I'm going to require that this graph has constant in degree, just so each new pebble that I place on the graph really corresponds to one unit of computation in the real world. And then I also want to make sure that the cumulative cost of pebbling this graph G is at least n squared divided by tau for some value tau that hopefully is as small as possible. Now, why do I want to make sure that cumulative cost is high? Well, here note that n denotes running time. Users are impatient, right? So we're kind of constrained. N has to be small enough that you can finish hashing in 1 second, half a second. And we also want to make sure that the attacker's costs are as high as possible, right? So we want the cumulative cost to be as large as possible. So in particular, we're going to require that cumulative cost is at least n squared divided by tau, hopefully for some small term tau. Okay. So now I guess the key point, there's this combinatorial property called depth-robustness, and you can show that it's both necessary and sufficient to build a secure data-independent memory hard function. All right, so let me tell you what depth-robustness is. Right, so you have a directed acyclic graph, and we'll say that it's ED reducible if you can find a subset of E nodes such that deleting these nodes from the graph reduces the length of the longest path to be at most D. Now, okay, that's a mouthful, but let me show you a quick example of a 1-2 reducible graph. So 1-2 reducible means that I should be able to delete one node and that the longest path remaining in the graph should be 2. All right, so can anyone tell me here how to show this graph is 1-2 reducible? So I have to find one node to delete to reduce the depth of this graph to 2. What? Okay, yeah, so exactly. If I delete node 3, then I've gotten rid of all these edges that are incident to 3. So now there's 2 paths remaining in the graph. There's the path from node 1 to node 2, and the path from node 4 to node 5. So there's 2 paths left in the graph, but each of these paths has length at most 2. So in this case, we say that the graph is 1-2 reducible. Now, if a graph is not reducible, we say that it's depth robust. Depth robust means that for all subsets of size E, deleting E nodes is going to leave a path of length D remaining in this graph. Right, so on the one hand, we have reducibility, and if it's not reducible, we'll say that it's depth robust. Okay, so why do we care about this strange combinatorial property? Well, it turns out that if your graph is ED reducible, then there's an attack, right? There's a pebbling strategy that has low cumulative cost. In particular, if your graph is ED reducible, then there's a pebbling strategy with this cost. So E times N plus, then there's this weird, square root of N cubed times D term here. I'm not going to go into details where those particular terms came from right now. But intuitively, why does it matter that the graph is ED reducible? Well, if the graph is ED reducible, that means there's a small set of data values that you can store that compress the graph, right? So if you just you have a small subset of nodes, and if you just store the corresponding data labels, then any remaining path in this graph must be short, which means that any data label that you don't have stored in memory, well, it's not stored in memory, but at least you can recover that data value fairly quickly, right? Because there's no long path in that graph, and a path corresponds to a chain of data dependencies, right? So if you can find a smaller set of nodes to delete, which really reduces the depth of this graph, then that gives the attacker a way to actually attack, right? He can store these values in memory and discard other values from memory to save space. But later, when he needs to recover those values, there's a very efficient way for him to recover any discarded data values. So one thing to note is that if E and D are smaller than N, then in particular, this means that the cost is substantially smaller than N squared, right? So we want to have costs that scale with N squared. But if E and D are both smaller than N, then this actually gives us an attack with costs that's substantially smaller than N squared. Okay, so now for an attacker, the natural question to ask is, okay, well, depth robustness is necessary to have a secure data-independent memory hard function. So we have all these candidate memory hard functions. Are they actually based on depth-robust graphs? So we started to look at the question, and the answer is a resounding no. These graphs are not depth-robust. So in particular, we found that Catena is basically E n over E reducible for any value E that you pick. Now, if you take a chain, if your graph is just a chain with a link from node 1 to node 2 to node 3, et cetera, and no other edges, this graph is E n over E reducible. So this is basically as reducible as you can possibly get. In terms of depth robustness, it doesn't get any worse than this. And that gives us an attack with complexity n to the 1.62. Again, don't worry about the particular exponent, but the fact is that this graph is reducible, and because it's reducible, you can get more efficient pebbling attacks. So balloon hashing and an older version of Argon 2I are E, and then we have n squared over E squared reducible. Okay, so now that might look a little bit confusing, but here if we plug in, let's say E is n to the 3/4, then that means that E is n to the 3/4 and D is n to the 3/4. So in this case, E and D are both substantially smaller than n, and once again we get significant attacks. And if you optimize these attacks, basically what you get is cumulative cost at most n to the 1.71. So again, the target here is n squared, and we're getting something substantially lower than n squared. Now, the latest version of Argon 2I is actually a little bit better. So it's now n cubed over e cubed, e comma n cubed over e cubed reducible, which is a little bit better than Argon 2I earlier version. So in particular, now we still get an attack. It's not quite as good, but it's still substantially better than than an attack that has cost n squared. So in every case that we've looked at, the resounding answer is no. These graphs are not depth robust, and because they're not depth robust, we can actually get amortized attacks, which would reduce the attacker's cost significantly. Yeah, there's other iMHF candidates, and I'm not going to introduce them, but similar results hold for all these other proposals. So yeah, in particular, Argon 2 was the winner of the password hashing competition, and Argon 2I is the variant that the developers recommended using for password hashing. I should mention that this attack only is on Argon 2I, the data independent mode, but the data independent mode is the version they recommended because it's not vulnerable to these side channel attacks. Okay, so that's the bad news. Let me tell you about some of the good news. So the good news is if you're trying to design a secure data independent memory hard function, it's actually sufficient to start with a depth robust graph. And once you have a depth robust graph, you immediately get a construction of a secure data independent memory hard function. So in particular, if your graph is ED depth robust, then the cumulative cost to pebble this graph is at least E times D. Now, the implication immediately is there exists graphs. This goes back to work of combinatorialists like Paul Erdos and Semiretti back in the 1970s. So there actually exists graphs that are ED depth robust with E equals n over log n and D equals n. So in this case, you get a construction with cumulative cost at least n squared over log n, which is still not quite n squared, but fortunately it's a lot better than n to the 1.75, or I think it was n to the 1.77 for Argon 2I. So this is nice. It's getting us pretty close to that ideal goal. And there was another theoretical result before this, which got n squared over log to the 10 times n. But this was a theoretical result, and if you actually calculate log to the power 10 n for practical values of n, it turns out that log to the power 10 of n is bigger than n squared. So for a theoretician, they're looking at this and saying, well, this term grows much faster than this term, but for a practitioner, log to the 10 actually grows pretty quickly. Okay, so I guess a little bit more bad news. It turns out this is actually the best you can hope for. You can't actually do better than n squared over log n if you want your graph to have constant in degree. So it turns out that there's a matching attack that shows that any any constant in degree graph, has cumulative cost at most n squared. I guess there's a log n factor, but log n over log n. So basically, up to small, log n factors, this is tight. Okay, so now something you might have noticed on this slide. The implication here is that there exists a constant in degree graph. Right, so this was, this result appeared in a Eurocrypt paper, and it's an existential result. It means that there exists, a constant in degree graph with this security property, but it doesn't mean that we actually have, a practical instantiation that we can use. After all, the construction is based on, 1970s work of Erdos, Graham, and Semeretti. It turns out that, these guys weren't particularly concerned about, the practical ramifications of this graph. They were just interested in the combinatorics. Right, so all this is saying is that there exists a constant in degree graph with this property, but it doesn't say that there's anything that we can actually use in practice. So a little bit more good news. There's an upcoming CCS paper where we actually show that not only does there exist a constant in degree graph, we actually give a practical construction of a constant in degree graph, which is n over log n and depth robust. So this is maximally depth robust. This is the best you can hope for, and the cumulative cost is at least n squared over log n, which is again the best you can hope for. So what do I mean by practical? Well, what I mean by practical is that you can actually tweak the Argon 2i source code to use the edge distribution from this new graph. And if you actually make these modifications and just evaluate performance empirically, there's no adverse effect, right? It runs in exactly the same amount of time. It's actually marginally faster, but that, very marginally faster. So basically, you get the same performance if you make these changes. So now we've gone from just an existential result to an actual concrete result that you can implement. Now I should mention one of the key challenges that remains is the constants that go into this lower bound are not particularly well understood. So a practitioner might still complain that you have this lower bound, but the best constants you can prove are not that great. And I'll be honest about that. I'm not going to claim that they're great constants. These are small constants here that we're able to prove it for. On the other hand, you can conduct an empirical security analysis. So empirical security analysis, I mean, just take the best known attacks on data-independent memory hard functions and actually run them. So for a concrete memory hardness parameter, so here, when n is 2 to the 20, that corresponds to about a gigabyte of memory. So you're looking at a data-independent memory hard function that fills a gigabyte of memory and takes roughly 1 second to finish. In this case, you can see that we're getting attacks of quality, 8 or higher against Argon 2i. But the best attacks that we can find against this new depth robust construction have quality around 3. And this even holds up to 16 gigabytes of memory. So the best known attacks still have quality 3, which means that the attacker's costs are only 3 times smaller than the costs of the honest party. Whereas here for Argon 2IB, there's an attack with quality, I think this is like 13 or something like that, right? So that means that the attacker's costs are going to be 13 times smaller than the cost of the honest party, right? So in this case, this is the best we can do. The attacker is going to get some advantage because he's parallel and he's running on an ASIC. But in practice, it seems like we can reduce this advantage from something like 13 to something like 3. So this graph shows that not only are these schemes theoretically more secure, they also seem to be more secure in practice, which is nice. So it's not just it's just not just an asymptotic result. The theory actually does seem to correspond to reality. So I should point out here that as we go down here, this is more secure. So on the y-axis here, we have attack quality, which is just the ratio, right? So this is the attacker's amortized cost divided by the cost of the honest party, right? So higher attack quality means that the attacker's costs are substantially, or sorry, it's the inverse. It's cost of the honest party divided by amortized cost of the attacker. So higher attack quality means that the attacker's costs are smaller and smaller. Okay. So let me step back, and I want to tell you about some of the newer results in memory hard functions. So I mentioned the difference between data independent versus data dependent memory hard functions. And I mentioned that SCRYPT was a data-dependent memory hard function. So we've seen that the advantage for data-independent memory hard functions is that there's no side channel attacks. The disadvantage, of course, is that the cumulative cost can be at most n squared over log n. Now, data-dependent memory hard functions have the disadvantage that they're potentially vulnerable to side channel attacks. But do they have any advantages? And the answer is yes. So this was proved at Eurocrypt 2017. It turns out that SCRYPT actually has cumulative memory complexity scaling with n squared. So if you run in time n, the attacker has to keep n units of memory allocated for n units of time. There's just no way around it. Now, the weakness of SCRYPT is that it's vulnerable to side channel attacks. So if there is a side channel attack, then the cumulative cost of checking each password guess drops dramatically. So you go from cost n squared down all the way down to cost n. That's not such a great situation. So Argon 2, in response to some of these new attacks, they've developed a hybrid mode. So basically the idea is you're going to run data independent mode for n over 2 steps. And then you're going to switch to data-dependent mode for the remaining n over 2 steps. And the idea here is if there's a side channel attack, you can reduce costs, but only somewhat, right? So here, if there's a side channel attack, costs reduce, but only to n to the 1.767, which is a lot better than SCRYPT, right? SCRYPT costs reduce dramatically all the way down to n. So this is, this is nice. It kind of gives you the best of both worlds, and it appears that, without a side channel attack, that the cost is still n squared. So I would actually propose, instead of, Argon 2 ID, use Argon 2 ID, but replace the graph structure with this depth-robust construction. And in this case, you're going to run in data-independent mode for n over 2 steps as before. If there's a side channel attack, now we have the property that cost only reduced to n squared over log n. So there's a little bit of a reduction in cost, but it's not substantial. So this is what I would actually recommend. There is an implementation of it on GitHub. Oh, I guess I didn't throw the link on here, but it's practical. I think it's practical graphs. If you search for it on GitHub, you should be able to find modified Argon 2i source code. And I would again recommend basically running Argon 2 ID, but with with this new depth-robust modification. All right. So in summary, right, you have lots of different options for password hashing. One option is just to use something like SHA-1, SHA-2, SHA-3. That's definitely a bad idea. It's just the cost of computing this function is just too cheap for an attacker. Then you have constructions that are based on hash iteration, like bcrypt, password-based key derivation 2. I would argue that these functions are no longer sufficient for password hashing. So they still seem to be deployed commonly in real life, but I would make the case that these hash functions are no longer sufficient to actually protect passwords. So Argon 2i, despite attacks, it's still an improvement over bcrypt and password-based key derivation function 2, but it still does have its flaws. Argon 2 ID is currently the mode of operation that the Argon designers are recommending. So if there's no side channel attacks, then it resists all known attacks, and it seems to have cumulative memory cost n squared. And side channel attacks reduce the security, but only a little bit. And finally, what I would recommend is using their construction, but replace the Argon 2I part with depth-robust graph. All right, and memory hard functions are an active research area. Something I'm working on quite actively at the moment. If you are interested in learning more, come talk to me. If you want to get involved in research in this area, always happy to chat. All right, so with that, thanks for listening, and I can take any questions. Yeah.
Go ahead and use your microphone, please.
Is it only applicable to ASIC chips or even FPGAs?
The technique is meant to design to defend against an attacker with an FPGA or an ASIC. I was using ASICs as an example, but yeah, an attacker might use an FPGA, and memory hard functions are also a good defense against any architecture, whether it's GPUs, FPGAs, ASICs.
On the amortization and doing parallel processing, was there? I mean, you showed the graph, but as a practitioner,
yeah,
would you say that some of the things that are used for like Bitcoin mining, some of the ASIC that you showed, or how realistic is the attack on some of the hash algorithms that won for the past hashing competition? Like, how realistic is it for, what type of attacker is it within their reach? Would you say like currently, and then I know you're looking into the future, but
no, that's an excellent question. The answer is that ultimately no one's actually built an ASIC with this attack, right? So there's no ASIC implementing the attack, at least not that I know of. Now, with that being said, there are a couple challenges that you would have to deal with before you built an ASIC. One is just the bandwidth overhead on the chip, right? So we tried, when we simulated the attacks, we tried to actually estimate, how much bandwidth would be required to run this attack, under different parameters. And we generally found that the attack was still successful, even if you constrain bandwidth. To do that, do those calculations, we were just looking at, a couple different chips and pulling the estimated bandwidth off them. There's plenty of work to be done to actually, look at the economic cost of implementing these attacks, and I won't claim that that's resolved. I can only tell you that there are groups that are looking into it at UCSB and at MIT, but I don't know the outcome of all their analysis yet. All right. Thanks.